this video, we are approximating area using rectangles. And we will approximate area using the left and right endpoints of subintervals and a finite number of rectangles. And then we will also find upper and lower sums with a general number of rectangles, which we'll label with the variable n. So here's the idea. If you're trying to find the area under a curve given by y equals f of x, between the vertical lines x equals a and x equals b, so we're trying to approximate this area. One way we can do that, and one way that we can approximate it, is we can take this interval from a to b and we can subdivide it into n subintervals of equal width. And that width we're going to call delta x. It's a tiny change in x. And then on each subinterval, we'll choose an x value and we will evaluate the function at that x value. Let's say I choose the x values on the right. So those are right endpoints of each subinterval. I evaluate the function at that x value on the right, and then I create a little rectangle. And then I do the same thing over here and create a rectangle. And then the same thing over here and I create a rectangle. And then over there. And then over there. And then there. And then I add all of those areas together and I say that's approximately equal to the area under the curve. Now sometimes those rectangles are going to lead to an overestimate. Like the area of these rectangles over here is larger than the area under the curve for each of those subintervals. But over here, the area of the rectangle is an underestimate of that area under the curve. Sometimes that overestimate and that underestimate sort of balances out and it gets us closer to the true area. And sometimes not, as we'll see in some examples. But that's the idea. We're approximating area under the curve with a finite number of rectangles, and n is the variable that we use for the number of rectangles. And so let's do this with a given value for n. Let's say someone asks you to use the left and right endpoints in the given number of rectangles to find two approximations of the area between the graph of the function and the x-axis over the given interval. So we've got this function, and we're on the interval from 0 to 2, and n equals 4. So the first thing that I would do, the first thing that I recommend all of you do, is start by sketching the function. We know that that's a parabola. It's been vertically stretched by multiplying by 3. That makes it 3 times as tall as it used to be. And then we move the whole thing up 1 unit. So when x is 0, y is 1. And then when x is 2, y is 3 times 2 squared. 2 squared is 4. 4 times 3 is 12. Plus 1 is 13. So this is not just scale. And we know it's symmetric, so it's going to be 13 at -2 as well. The function looks roughly like this. And my goal is to approximate the area between this function and the x-axis on the interval from x equals 0 to x equals 2. So what we're trying to do is we're trying to find the value of this area right here. We're asked to find two approximations, one using left endpoints of subintervals and one using right endpoints of subintervals. And we're told to make 4 subintervals. Okay, so the first thing that I would do with a problem like this is I would, after sketching this region, so first thing I do is sketch the region. The first thing I do after sketching is I compute delta x. That's the width of my subinterval. And delta x can always be found using this formula. It's the length of this subinterval divided into n equal pieces. So we'll take b minus a, that's the length of the subinterval, and we'll divide it by n. Since n is given to us, this is pretty simple. We just have b minus a over n is 2 minus 0 over 4, which happens to be 1/2, which is consistent with our intuition, I think. And then we will compute the endpoints of the subintervals. Now, generally, we'll use this notation for the endpoints. X sub 0, that's our first endpoint. That's always the value of a. That's exactly where we start, at x equals a. And then after that, we're just going to add delta x every time. So the first time, we'll add delta x times I. Or excuse me, we'll just add delta x, and we'll just have 1 delta x. So I'll go from x equals 0, and then I'll add delta x, which is 1/2, and that will get me right here. That's x sub 1. And then to get x sub 2, I add delta x again. So I've added delta x 2 times, so I'll be here. To get x sub 3, I add delta x again, so that'll give me right here, and then I add delta x a 4th time to get there. So in general, the first one is just a, and then x sub I is equal to this for I equals 1 through n. And you can see that if I equals 0, you actually get that one. So we could use this formula for I equals 0 through n to get all the subintervals. If there are 4 rectangles, you're going to have, I said subintervals, I misspoke. We're going to have 5 endpoints. This formula works for all 5 endpoints starting at I equals 0, excuse me. So we'll have, if there are 4 rectangles, we'll have 5 endpoints. We'll have that first one, x sub 1, x sub 2, x sub 3, and x sub 4. Okay, so we've got x sub 0 is 0. X sub 1, we add 1/2. X sub 2, we add 1/2 again. X sub 3, we add 1/2 again. X sub 4, we get 2. Notice that we start at A and we end at B. That's exactly as it should be. Okay. And now we're asked to approximate the area under the curve using left endpoints and right endpoints. So let's do left endpoints first. So I'll say approximate. Well, what I do in this case is I create rectangles over each of these subintervals. I go to the left endpoint, I evaluate the function there, and then I make a rectangle that has the function value at the left endpoint as its height. And then we do it again. And then we do it again. And then we do it again. Notice that this is going to give me an underestimate of the area under the curve. These 4 areas are less than that total area under the curve. There's all this area that we're missing. That's okay. That total area is approximately equal to this. That's f of 0 multiplied by 0.5. So that's the width of that subinterval. It's just length times width, plus f of 0.5 multiplied by 0.5, plus f of 1 multiplied by 0.5, plus f of 1.5 multiplied by 0.5. And that's it. We have 4 rectangles. We don't have f of 2 multiplied by 0.5 because there's no rectangle over there. It's not giving us area under the curve if I'm using that left endpoint. Okay, and each of these 0.5s that I filled in, those were in general, those were delta x's. Okay, so if you want, you could factor out the 0.5 from everything and then just add f of 0, f of 0.5, f of 1, and f of 1.5. And that would give you area as well. It's the same thing. It's just this in a shorter form. So I just need those function values. So if I want to use left endpoints, I need these 4 function values. So we're computing f at the endpoints. F of 0, f of 0.5, f of 1, f of 1.5. And I think I'm going to need f of 2 for the right endpoint, so I'll calculate that here as well. So I evaluate at all of those x values, x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. And so we get 1 and 1.75 and 4, and this one happens to be 7.75, and this one is 13. So for our left endpoints, we're using these first 4. So we've got 1 plus 1.75 plus 4 plus 7.75 times delta x, which is 0.5. And that happens to equal 7.7 or 7.25 square units. Now that's an underestimate of that area under the curve. So we know the area is probably more than that, or we can see that it's got to be more than that, but we don't really know how much more. If we wanted a better approximation, instead of doing 4 rectangles, maybe we should do 8, maybe we should do 100. With computers, it's possible to do things like that. We could also come up with a formula for this, and we will in a little bit. So that's the area under F using left endpoints and 4 rectangles. Let's do the same thing for the right endpoints. So we've got something that looks like this. And now we're using the right endpoints on each interval. We evaluate the function at the right endpoint, create a rectangle. At the right endpoint and create a rectangle. At the right endpoint and create a rectangle. And then we add up those 4 areas. Now this is going to give us an overestimate, as you can see. And using the right endpoints, the first function value that we use is f at 0.5. So we skip this one. And I've got f at 0.5 times delta x plus f at 1 times delta x plus f at 1.5 times delta x. And then we've got f at 2 times delta x. And if we factor out that delta x, we see we've just got to add those function values together and then multiply by delta x. So we get 1.75 plus 4 plus 7.75 plus 13 times that 1/2 times that width, and that turns out to be 13.25 units squared. So the area is somewhere between 7.25 units squared and 13.25 units squared. And if we want better approximations, we just take more rectangles. But we can see each time we do this, as long as we're using left endpoints, because our function's increasing, we're going to get an underestimate. Since our function's increasing, if we use right endpoints, well, the function's going to be largest on the right, so we're going to get an overestimate. And that leads us to something called upper sums and lower sums. So let's talk about that. And then we'll calculate the upper sums and lower sums for that function that we were just looking at. So upper sums are overestimates of area. And they're found by adding the areas of what are called circumscribed rectangles. And circumscribed rectangles are just rectangles that extend outside the area being approximated. And I know that there are lots of rectangles that extend outside the area being approximated. But we also want the rectangles to have a certain value. So this is how we'll define it. Let's say we've got a function that looks like this. And this is x equals a. And this over here is x equals b. And we want this area between x equals a, x equals b, y equals f of x, and the x-axis. We're trying to find this area right here. If we take that interval from a to b and subdivide it into n subintervals of equal width, and that equal width is delta x. It's notated by delta x, which is b minus a over n. I'm taking this interval, I'm subdividing it into n rectangles. So I take it and I divide it by n. That's going to give me delta x. Now, if our function f of x is a continuous function, on each of these subintervals, it's guaranteed to have an absolute maximum and an absolute minimum by the extreme value theorem. If I let m sub I be the x value on the ith subinterval, where f attains its maximum value, then the upper sum is defined this way. It's the sum as I goes from 1 to n of f evaluated at those m sub I. So this is the maximum value of f on the ith subinterval. And we multiply it by delta x. So I go to this subinterval, and the maximum value on that first subinterval occurs on the left. So I'll make a rectangle like this. Over here on that next subinterval, the maximum occurs on the left. So I'll evaluate there and make that the height of my rectangle. On the next one, the maximum occurs on the right. The next one, the maximum occurs on the right. And the next one, the maximum occurs on the right. And then on the last one, the maximum occurs on the right. Okay, so that's going to be the upper sum. And you can see that the area of those rectangles is always going to overestimate the area under the curve. Now the lower sum is kind of exactly what you would expect. We're going to use lowercase m to denote the x value on that subinterval. Where f attains its minimum value. Then the lower sum is given by this formula. It's the sum as I goes from 1 to n of f evaluated at those x values that yield minimums times delta x. This is the minimum value of f. On that subinterval. Okay, so upper sums are overestimates of area found by adding the areas of circumscribed rectangles. See how their areas extend beyond that region. Lower sums are similar, just sort of the other way around. Those are going to yield over or underestimates of area. And the rectangles that we're looking at, we're going to call those inscribed rectangles. Those are rectangles whose heights are given by the function, but they lie entirely inside the area being approximated. Okay, so for my lower sums, I go to each subinterval and I find the minimum value of the function on that subinterval and I draw a rectangle. So for this first interval, the lower function value is on the right. Here the lower function value is on the right. Here the lower function value is actually in the middle. Here the lower function value is on the left. Over here, the lowest function value is also on the left. And over there, the lowest function value is on the left. And so we add all of those together. And that's giving us an underestimate of the area under the curve, which is given by this right here. Now, we are going to tend to look at functions that are either increasing the whole time or decreasing the whole time. If a function's increasing over an interval or decreasing over an interval, then we say, it turns out that the lower sum and the upper sum correspond to sums found by using the left endpoints and the right endpoints. So let's say our function's increasing. If f is increasing and we're on the interval from a to b, and I subdivide that interval from a to b into n subintervals of equal width. If the function's increasing, that means the smallest y value is going to be on the left in each subinterval. So the left endpoints are going to give me an underestimate. The left endpoints will correspond to inscribed rectangles, and that will give me the lower sum. f is increasing, the largest y value on each subinterval will be on the right. So if I evaluate the function on the right, and I do this, the right endpoints will correspond to an upper sum. So that's what happens if f is increasing. Now, if f is decreasing, it goes sort of the other way around. Well, exactly the other way around. If I use the left endpoints on each interval over here, left endpoints lead to overestimates. So in this case, left endpoints give you an upper sum. This is only if the function is decreasing. And if I use the right endpoints instead, well, since the function's decreasing, that's going to be the smallest y value on the interval. So the right endpoints will correspond to lower sums. Now, I don't have any of this memorized. I don't recommend that you memorize it. I just recommend that you understand the concept well enough to draw this picture and see which one would give you the upper estimate and which one would give you the lower estimate, or the overestimate or underestimate, or the upper sum or lower sum. The notation that our textbook author uses for each of these is capital S sub n for upper sum and lowercase s sub n for lower sum. Now, if the function's not increasing or decreasing the whole time, if it's more like this, it switches. When it's decreasing, using the left endpoints leads to an overestimate. When it's increasing, using the left endpoints leads to an underestimate. You sort of get a mix of each of those. You won't be asked for lower sums or upper sums in cases where the function looks like this. You'll only be asked for upper sums and lower sums in the cases where the function's increasing or decreasing. So you'll get to choose either the left endpoint or right endpoint, depending on what that graph looks like. Okay, so let's look at an example now. Let's actually calculate some upper and lower sums. And this time we're asked to leave the answers in terms of n, the number of subintervals. And of course, the number of subintervals is the same as the number of rectangles. So our function is 3x squared plus 1. We're on the interval from x equals 0 to 2, so that's our a, and that's our b. And we want this in general for n rectangles. So let's look at our picture again. Looks roughly like this. We want this area under the curve right here. So first of all, I notice my function is increasing. So that means that if I use the left endpoint of each subinterval, I'll get a lower sum. So left endpoints correspond to lower sums, and right endpoints, oops, correspond to upper sums. Okay, we can calculate whichever one we prefer first. Doesn't really matter. I think I will start with, I'll start with the upper sum and then we'll do the lower sum. Okay, so the way you want to start all of these problems is you start by doing this, identify which endpoints would give you an upper sum and which ones would give you a lower sum by looking at your picture. Just graph it, see if the function's increasing or decreasing, and then evaluate the functions at left endpoints and right endpoints and see what that correspondence is. And then the next thing we do is we compute delta x. Now this time we're computing delta x in general. We're going to leave it as a function of n. Basically, we're coming up with delta x as a formula in terms of the number of rectangles that we want to use. That way we can substitute in a number of rectangles later when we're done with all this. So we're leaving this in terms of the number of rectangles n. Delta x is still the length of that subinterval, or excuse me, the length of that interval divided by n. So we take b minus a and divide by n. This time we're leaving n alone. We're saying n is the number of rectangles. If n was 4, we'd have 4 rectangles. If n is 100, each of those widths would be 1 over 50, and we'd have 100 rectangles, and so on. And the next thing you want to do is compute the x sub I that you're going to use. And I think I'm going to use x sub I star because we used x sub I for the endpoints of each interval. X sub I star is just going to be the x value where you're choosing to evaluate your function. In this case, since we have decided to do the lower sums first, the lower sums correspond to left endpoints. So we're going to compute this. These are left endpoints. I'm going to give you a formula for this, but I want you to see where it comes from. So the left endpoint of each subinterval, or that first subinterval, is just the a value. It's exactly what we start with. So x sub 1 is going to be, or x sub 1 star is a. And I'm just putting a star on it because I want this x sub 1 to be different from the x sub 1s we looked at earlier. So that first left endpoint is just 0. Then to get the second one, we take a and we add delta x. So that's 0 plus 2 over n, so we just get 2 over n. To get the third one, do you see that we just add delta x again? Delta x plus delta x is 2 times delta x. So we're going to get 4 over n. So that's the pattern. But in general, do you see what happens? X sub I turns out to be a plus delta x times some number. When I is 1, I actually have a plus delta x times 0 because I haven't added any delta x's yet. When I is 2, we only add 1 delta x. When I is 3, we add 2 delta x's. So it looks like we have just added 1 less delta x than that subscript there. To get to that third subinterval, I added delta x twice. I started here, add delta x once to get to the next one, and then add delta x twice to get to the third one. So x sub I is a plus delta x times I minus 1, and this is for left endpoints. You don't have to memorize this. I will give this to you. So you're computing this And you would actually just look it up in the formulas. You'd say, okay, the left endpoint formula is this. And then you substitute in the value of A and the delta X that you just calculated. So you'll choose the appropriate formula. And substitute A and delta X. So A is 0 in this case because of the interval that we're on. Delta X was 2 over n. So I've got 2 over n times the quantity I minus 1. That's my x sub I, or I guess I should call it x sub I star. I'm just putting a star to say it's the chosen x value on that subinterval. Okay. And remember what we're trying to do. We're trying to find the sum of the areas of those rectangles. So now that we've got the x value and the width, we just need to find the height, and then we'll take the length and the width, or the length and the height, or the height and the width, excuse me, multiply those together to get the area of that one little rectangle. So let's do that. Oops. So we want to compute the area of the ith rectangle. We could call that A sub I. It's just length times width, and that's just the function evaluated at x sub I star, so that's a chosen x value, times the width, which is delta x. Well, our function was 3 times our x value squared plus 1. And then we just substitute in that x sub I star and the delta x that we calculated earlier. For our problem, x sub I was 2 over n times I minus 1. And we're squaring that. And then delta x was 2 over n. So that's our area. It's probably simpler to move on from here if we simplify this first. So let's simplify it. I'm thinking of that as itself over 1. So we want to square the 2, square the I minus 1, square the n, and simplify, and then distribute the 2 over n to everything. So we've got 3 over 1 times 4 times I minus 1 squared. In the denominator, you've got an n squared, and then a 1 here. And then you distribute the 2 over n to everything. Let's distribute here. We've got 12 times I minus 1 squared. That's I squared minus 2n plus, or 2i, excuse me, plus 1 over n squared. I'm going to write that twice in FOIL. Plus 1 times 2 over n. And then distribute 2 over n times this. So that's going to give me a 24 there and an n cubed in the denominator there. Plus 2 over n. Now that's the area of the ith rectangle. And remember, we have n of them because we have n subintervals. So the upper sum I say upper sum? I think this is the lower sum. Yeah, we're using left endpoints, so this is a lower sum for our case. In our case, excuse me. So the lower sum, that's just a sub 1 plus a sub 2 plus a sub 3 all the way through a sub n. Well, we know that. We know sigma notation. That's the sum as I goes from 1 to n of the a sub I. So we want to compute this. Well, we could first of all just state it. It's the sum as I goes from 1 to n of a sub I, and a sub I is what we just calculated. So we sub that in. And we can divide each of these terms by n cubed. I think I will. It's 24 over n cubed times I squared minus 48 I over n cubed. And then I've got a 1 over n cubed. That's that. Plus 2 over n over here. Okay, that's after distributing or dividing each of those terms by n cubed. And I can simplify this. If I want to write this without sigma notation, I can, using the formulas that we talked about in the last video. So this is actually the sum of 1, 2, 3 terms. This one has an I squared in it, and that one has an I in it, and these don't have any I's, so I'm going to split this into 3 summations. That 24 over n cubed is constant with respect to I, so I can factor it out. And then I have the sum as I goes from 1 to n of I squared, minus, over here, the 48 and the n cubed are constant, so I can factor that out. And I've got the i's, and I'm summing those as I goes from 1 to n. And there are no i's in this part, so I've got that over there. All right. Now I've got a formula for this and a formula for this, and that's constant with respect to I, so I've got a formula for that. Once I substitute those and then simplify, that's my simplified formula for the lower sum. The sum of the I squared is n times n plus 1 times 2n plus 1. We're dividing all of that by 6. Then over here, bring that 48 over n cubed down. The sum of the i's, that comes from Gauss. We have n times n plus 1 over 2. And then this is constant. If I've got a constant added to itself n times, I just get that constant times n. So I'll bring down my constant, and I'll multiply it by n. If you're saying it doesn't look constant to me, you're right, it doesn't look constant to me either. But we're treating n, that number of rectangles, as constant here, and then we're summing as I changes. So this is constant with respect to I, it's constant with respect to the summation, so we just bring it out. So this is our lower sum. It just hasn't been simplified. We can simplify it now. N goes into n cubed, n squared times. That n will reduce with one of those n's. You can distribute this n here and here. 6 goes into 24 4 times. 2 goes into 48 24 times. And so we end up with 4 times n plus 1 times 2n plus 1 all over n squared minus 24 times n plus 1 over n squared plus 1 over n squared, because that n and one of those n's reduces, plus 2. If you want, you can get a common denominator here. Could multiply that by n squared over n squared, so they all have a denominator of n squared. It's not necessary, but it can be done. We'll distribute 2n times n is 2n squared times 4 is 8n squared. Outer times outer and inner times inner is 3n times 4 is 12n. Last times last is 4. Distribute the negative 24 here. Okay, and now I've got 8n squared plus 2n squared. That's 10n squared. 12n minus 24n is negative 12n. And then I've got a 4 minus 24 is negative 20, plus 1 is negative 19 over n squared. Now that is my lower sum. That's an underestimate for the area under the curve. Now this is a lower sum in terms of the number of rectangles n. So if I had 100 rectangles, which I really wouldn't want to draw personally, I could still find the lower sum by just substituting in n equals 100 to this. And I might simplify that. 10n squared over n squared is just 10. Then one of the n's will reduce there. So we'd get that. So we'd have 10 minus 12 over 100 minus 19 over 100 squared. And let's see what that is. So about 9.8781. Well, actually, that's exactly what that is. Calculator gives exact answers. So that is the lower sum with n equals 100 rectangles. Okay, so now let's do the upper sum. Left endpoints corresponded to a lower sum because our function was increasing. The right endpoints correspond to an upper sum. So we start in the same way. You compute delta x, but now instead of using x sub I star, instead of using the left endpoint formula, we want to use a right endpoint formula for x sub I star. So you compute delta x, then we compute x sub I star using the right endpoint formula. And then once you have that, you want to find the area of the ith rectangle. And the area of the ith rectangle is just, I wrote first, it's ith. It's just that function value at that chosen x value, x sub I star, and then we're multiplying it by delta x. So delta x is b minus a over n. That hasn't changed. It's still 2 minus 0 over n. So we've got a width of 2 over n. So n is 100, that's 1 over 50. Then for x sub I star, this time we're using right endpoints. Trying to find my picture. Actually, let's look at this picture from the very beginning. If I'm using right endpoints this time, that first x value is not a, but it's a plus delta x. That second x value is a plus delta x plus delta x. So to get to the second one, we had to add delta x twice. The first one, we added delta x once. Second, we add delta x twice. Third, we add delta x 3 times. So the formula for the right endpoints is a plus delta x times I. And all you do is you substitute in the a value, that x value where you started, and the delta x. That delta x that you just computed. So we've got 0 plus delta x, which is 2 over n times I, or you could call that 2i over n. Okay? And now we want these areas, the area of one of those rectangles. So that's f evaluated at x sub I star times delta x. And x sub I star is 2i over n, and delta x this time is 2 over n. And remember what our function was. It was 3 times that x value squared plus 1. So I just take my x value, I sub it in, I square it, I multiply by 3, I add 1. That's the height of my rectangle. Then I multiply it by the width. And it's simpler if we simplify this first, so I'll write that as 3 over 1. Square each of the factors separately. And then we've got 12i squared over n squared. And we're multiplying by 2 over n. So distribute that 2 over n to everything. And you get 24i squared over n cubed plus 2 over n. That's nice. It's going to be simple little summation to simplify. So that's the area of one rectangle, but we want the area of them all. So we want to compute the upper sums now. The upper sums are given by the sum of those areas. It's the sum as I goes from 1 to n of the a sub I. But these are the a sub I, so we just substitute those in. Okay, and now I want to use my summation formulas and the properties of summations to simplify this. So I see I've got two terms, so I can split this into two sums. I have the sum of the first term plus the sum of the second term. Now over here, that 24 over n cubed, that is a constant, so I can bring it out. Then I've got an I squared there. Well, I've got a formula for this, and these are constants with respect to I, so I've got a formula for that as well. According to our formula, I squared is, or the sum as I goes from 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. So we substitute that in, and the sum as I goes from 1 to n of a constant is that constant n times, so we get that constant multiplied by n. Those n's reduce, 6 goes into 24 4 times, n goes into n cubed, n squared times, and you end up with this. You've got 4 times n plus 1 times 2n plus 1, all over n squared plus 2. And you could leave it like that if you want to. You could get a common denominator if you want to. Either one is fine. I think I'll get a common denominator. If I distribute, 2n times n is 2n squared times 4 is 8n squared. I've got outer times outer and inner times inner is 3n times 4 is 12n. Last times last is 1 times 4 is 4. Then we add the 2n squared. So that and that are like terms, so we can combine them, and we get this. So this is the upper sum. Or if we simplify, just divide each one of those by n squared. We get 10 plus 12 over n plus 4 over n squared. This gives me the upper sum, that overestimate of that area under the curve for the number of rectangles n. So our upper sum with, let's say, 100 rectangles is given by this. It's 10 plus 12 over 100 plus 4 over 100 squared. So we get 12.1204. Now we had a lower sum, we did that earlier. It turned out to be 10 minus 12 over 100 minus 19 over 100 squared. That was 9.8781. So the true area, the actual area under the curve given by y equals 3x squared plus 1 on the interval from A to B, that area between that curve and the x-axis, is somewhere between 9.8781 and 10.1204. It's somewhere in there. We got pretty close. Now, if you want a better approximation, you just tend to take more rectangles. You say, well, what if I had 1,000,000 rectangles? Well, if I had 1,000,000 rectangles, then I'd have 10 plus 12 over 1,000,000 plus 4 over 1,000,000 squared. And then I'd replace this 100 with 1,000,000, and that would be 1,000,000 squared. And we could get an even better estimate. So that's how that works. Let me see if I can't go to my first page. Yeah, I don't know where it went. There it is. So we can approximate the area under the curve using left and right endpoints and a finite number of rectangles. If they tell you that n equals 4, this is actually pretty simple. All you do is you find the delta x, b minus a over n. They're going to give you a number. You're going to find out how wide those rectangles are. Then you find the x values at the ends of each subinterval. X sub 0 is always a. And then you just keep adding delta x to get the other ones. If you want a formula for that, it's this. And for I equals 0 through n, that'll give you all of them. And then the left endpoints just come from using x sub 0 all the way through x sub n minus 1. The right endpoints come from using x sub 1 all the way through x sub n. And you just find areas of rectangles, length times width, length times width, length times width, all the way across. Add those together, multiply by the widths, and you get an approximation for area. Use the left endpoints on one of them and the right endpoints on the other. If the function's increasing or decreasing, one of those will be an overestimate and the other one will be an underestimate. Now, for upper sums and lower sums, well, we handled this a little bit differently. With upper sums, we're evaluating the function at an x value that leads to a maximum. We want the maximum value of that function over the interval. That will always lead to a circumscribed rectangle and an overestimate of the area under the curve. For lower sums, we're using these blue rectangles. So that's where we're evaluating the function at an x value that leads to the minimum value of that function being that height. And those rectangles are always inscribed. It's always within that area under the curve that we're trying to evaluate. If the function's increasing or decreasing, one of those corresponds to the left endpoints and one of them corresponds to the right endpoints. The geometry will tell you which one is which. But in practice, what we do at this point, if we want upper and lower sums, is we find these areas, the same areas that we were calculating before with n equals 4, but we find them in general. So we compute delta x as a function of n. Then we compute the left endpoints using a formula. I'll give that to you. Or we compute the right endpoints using a formula. Then in each case, we evaluate the function either at the left endpoints or right endpoints. We simplify, and then we add all of those together. And then we simplify this formula using our formulas for summation that we studied earlier. And then we've got a formula that represents an overestimate of the area and a formula that represents an underestimate of the area. Yeah, the actual area lies in between that lower estimate and that upper estimate.